Take out your notes. Here we go. We investigate this meaning of a logarithm. Logarithm base a of x means the following. Base a to what power is equal to x? That's what we're trying to figure out. So if you see this piece, log base 2 of 32 is equal to 5, we're going to express this in exponential form. Yesterday we looked at exponents, exponential functions. Well, we say the base is 2, logarithms solve for exponents. I have an exponent of 5 is equal to 32. It's always good after you write it down to look at it and say, does that make sense? Does 2 to the 5th equal 32? Is that reasonable? Yeah. Yep. Yeah. So the next one would be what? 6 squared is 36. Does that make sense? Something 0 is 1. 3 to the 5th is 243. Well, what about the next one? Yeah. You see, something you need to know about logarithms is if you just see log, the base is 10. And if you see ln, the base is e. So in this situation, you have a base of e. You could write it, I guess, as log base e of e is equal to 1. So the idea is that e to the 1 is equal to e. Are you convinced that e to the 1 is e? Yeah. The next one would be what? You don't have to rewrite it using log. Just use natural log. So what's my base? E0 is 1. Is that, can you rationalize that? Does that make sense to us? Great. All right. Let's go backwards. Let's express these in logarithmic form. So we're going to say log with a base. What's my base? 2 of what? 16 is equal to 4. Excellent. You do B, C, D, E, and F on your own. Go. Okay, let's check it out. I got log of 100,000 is 5. We good? What didn't I write? Why? Assumed base. If you write base 10, that's fine, but you don't have to. Log base 8 of 1/64 is equal to -2. Log base 7 of 1 is equal to 0. Log of, or base 10, I didn't write the base 10 of 1/10 is -1. Is that the one you guys were having a discussion about? Oh, okay. All right. And then F, since I have E, I do natural log, because that's log base E of E is equal to, in fact, 1. Any questions on that? Flip it over. Okay. We would now like to evaluate a logarithmic expression, and we're going to show you a couple ways of doing this. Part of it will be new. Again, I'll just keep open eyes and minds to what we're going to do. Log base 4 of 64. Anybody know what it is? It's 3. Why? Right. This means 4 to what power is 64? And so the answer is 3. Okay, he says this is easy. So we got 3 to what power is 1/9? -2. We got 8 to what power is 8? Excellent. Now watch. There's another way of thinking about this type of problem. And I want you to know that you may always say, well, I'll just always do it that way. You guys, we're going to use this piece. So log base 4, 64 is the same as 4 cubed, correct? And 1/9 log base 3 is the same as 3 to the -2. And log base 8 is of 8 to the 1. Watch what happens here. Right? I have log base 4, 4 to the 3rd. What happens is these cancel out, and I'm given 3. That's the answer. Log base 3 of 3 to -2. Those cancel out. I have -2. Log base 8 of 8 to the 1 cancel out. I'm given 1. Now you said that doesn't. I mean, that just seems like voodoo math, doesn't it? Yeah. Let's because right now it just looks like we're making stuff up, doesn't it? Let's admit it. It just looks like we're just making it up. Like we're doing this right now, right? We're doing like a sine of x over n, and we're getting 6 out of the deal, right? Right? Yeah. Hey. I didn't use that joke that last hour. That could have helped things a little bit. It looks like we're making this stuff up as we go, right? You're losing confidence in your teacher. We're going to try to gain it back. Tenley is 8 years old. She's going to be 9 on Monday. Yay, golden birthday. Get her some gold, right? Gold, DeWalt. There we go. I tell Tenley someday, I'm like, Tenley, x plus 3 is equal to 8. Just subtract 3 from both sides. In fact, right now at this age, I'm guessing, because kids do show an early ability to handle algebra, I'm guessing that she can understand that those cancel and gives me 5, right? Because these are inverse operations. They undo each other. Agreed? Just like if you had 2/3 x is equal to 8, you would multiply by 3/2 because those undo each other. And that kind of makes sense. But then one day somebody came to you and said, well, square root of x is equal to 2.5. You want to get rid of the square root, you square both sides. And right now you're saying to yourself, yeah, of course you do. But folks, look at the symbols. I mean, is it obvious that those things should just somehow cancel each other out? You have to understand the operation of square rooting and squaring, correct? So then all of a sudden, Mr. Gens comes to you and we say, well, we're going to do this. What happens if you have f of x and you want to undo the function? Remember a couple chapters ago when we did function inverse? And you got x out of that. Well, folks, it turns out that if you have a logarithm with a base, and then you have an exponential function with a base, those are inverse operations, and they undo each other, giving you 10, because they are inverse operations. So I've tried to give you the background on those other things, just like you say, subtraction and addition. Okay, multiplication and division, function and function inverses. So therefore, logarithms and exponentials, those are inverse operations of each other. Okay, flip back one page in your notes so we can write this part down. Super crucial to our ability to move forward. Log base a of a to the x, those cancel, leaving you with x. And a raised to the log base a of x, those cancel, leaving you with x. It makes you feel uncomfortable to cancel them, but it's because they are inverse operations. We talked about inverse functions. I know you probably don't remember as much as I want you to, but we'll just move on. Look at letter D. So we take this kind of problem, like, what? We got log base 5 of 5 to the x plus y. What happens? Boom, x plus y. Now that one is one you can generally kind of think through, but the next one, I mean, you're going to really scratch your head trying to figure this one out, unless you understand that 3 and log base 3 are inverses. They cancel and give you 7. Isn't that sweet? Sometimes it's not as obvious, and you've got something like this. Natural log of 1 over e squared. Well, that's the same thing as the natural log of e to what power? -2. Natural log, what's the base of natural log? E. And so natural log and e cancel, giving you -2. Excellent. Good work. I'm going to let you start an assignment after we do this piece right here. You're going to have some time to kind of practice and try. But let's do this last part where we try to use our properties of logarithms and exponentials to be able to find x. Forgot the x there. Sorry about that. So the first one says log base 2 of x is equal to 3. Anybody know? You say 8. How'd you get that? You said base 2 cubed is equal to x. So therefore, x is 8. He is correct. You guys try B, C, D, E, and F on your own. Don't be surprised if one of them starts to make your mind hurt a little bit. Go. And hopefully it's pretty good. That's not us. So this one, you've got x squared is 100. So x was 10. Good. This was 5 to the x is 125, so therefore x was 3. Now, look at this one. This problem actually happened by accident. I was sitting down writing problems quickly, and as I associated 49 and 1/2, anybody know what I was coming up with in my head for a solution? 7, but that's not the answer. So Carson sees we got, so this reads x to the 1/2 is equal to 49. So I remember doing this problem in class. I was anticipating 7. I was writing down, like, well, there's no way the answer is 7. This is saying, what number do you take the square root of to get 49? What? 49 squared, which is like, what, 2,401? Yeah, big number. See that? Anybody get stuck on the next one? Man. 0? Yeah, you want to say 0, but anything to the 0 is 1. 0 minus 1, 2 to the negative 1. No, that's 1/2. Sometimes the situations make a lot more sense if you think of the graph. You're wondering, when is 2 to the x equal to 0? Yesterday, do you remember what 2 to the x looked like? Did it ever cross over the x-axis? Can it ever equal 0? Never. Never, no solution. No answer. Can't do it. And the last one was 10 to the negative third is equal to x. Well, 10 to the third is 1,000, so 10 to the negative third is 1 over 1,000. Very good. Okay, I don't have this problem in your notes, but if I were to write the notes over, I put one more problem in there, and then I'm going to let you work for a little while. What if I had this as a problem? Log base 9 of 27 is equal to x. That means 9 to the x power is 27. Kind of tough to think about, right? Sometimes we have opportunities to maybe look at the base and change it. Good idea. You're getting along the right idea. You're close. What number multiplies to both 9 and 27? 3. So would you agree that 9 is the same as 3 squared? And 27 is the same as? So all of a sudden, this is my equation, isn't it? Well, what do you do when you have a power to a power? Multiply. So I got 3 to the 2x is equal to 3 to the third. So now, those equations are going to be true whenever 2x is equal to 3. Yeah. So x is 3 halves. So sometimes you have to change the base in order to make that work out. You like that, you said? Yeah, it's kind of fun. You're going to get a chance to try it on your own. Look at your worksheet. You're going to get about 10 minutes here. Use that time wisely. Some of these are going to give you a run for your money. And just pause at them. There's for sure one we're going to do together in class. But I want you at least have to think about it and gut through it a little bit. Go. Exponents, logarithms, exponentials that make your brain work in different ways. If your brain hurts, it means you're getting smarter. Good job. Way to go. Oh, wrong class. Sorry. We're not ready for the mean value theorem. Let's just do it. Let's go. Okay, flip to the second to last page in your notes. Somebody tell me something, tell me anything about what you learned about an exponential function yesterday. If the base is greater than 1, it has that kind of shape. Excellent. What else did you learn? Base is less than 1, it goes the other direction. What'd you learn about the point that it goes through? Why does it go through 0, 1? So if you take something, because anything to the 0 power is 1. We talked about why that was. What was this thing here? Horizontal asymptote, what's the equation? Y equals 0. What did we say was the domain for these type of functions? All real numbers. What did we say was the range? 0 to infinity. Sweet. So what we want to do now is instead of graphing an exponential function, we want to graph a logarithmic function. And it actually starts with this. That's where we start. Because we said that the relationship between exponentials and logarithms is that they are, starts with an I, rhymes with versus, inverses. They're inverses of each other, right? Yeah. And in chapter 2, we talked about that when you have inverses, what do you do with x and y? What do you do with x and y? You swap them, right? So that's what we do. If this one had a asymptote of y is equal to 0, then this was going to have an asymptote of x equals 0. Cool. I'm figuring something out. If this one went through the point 0, 1, then this is going to go through the point 1, 0. Sweet. Let's roll. If this one had a domain of all real numbers, then this one has a range of all real numbers. And if this one has a range of 0 to infinity, this one's going to have a domain of 0 to infinity. Great. So I've got some really important characteristics figured out about this graph. Maybe the last piece that you don't remember quite as much is we talked about when you have these inverse functions, they're actually reflected over the line y is equal to x. They're reflected over that line. And so if we reflect that, we get that shape. That's your parent function graph for a logarithmic function. Now, if we change the base, that may stretch or shrink the graph, but don't worry about that. We're not trying to show that behavior. Some people get confused if you have natural log. Natural log is just a log base e. So you get the same type of shape, same type of properties as the previous one, okay? So, flip back to your notes. Right here, it says, find a function of the form y is equal to log base a of x, given the function passes through the following points. What do you notice that they have in common for the point that they all pass through? 1, 0. We just learned why that was, right? So what I have now is I'm going to focus on 25, 2. So we have, this is our x value, this is our y value. So it says that the y value is 2. So 2 is log base a of 25. So anybody know what a would be in this situation? A is 5. You write a is 5, you don't get the points on the test. Okay? Because you need to write the actual function. The function is y is equal to log base 5 of x. That's my function. Negative 1 is equal to log base a of 1/6. What number do you take to the negative 1 to get 1/6? 6. So therefore a is 6. So my function is y is equal to log base 6 of x. You do letters C and D on your own. Go. Silly Mr. Gantz. What number do you take to the 4th to get 10,000? 10. So you could write it as y is equal to log base 10 of x, but more commonly it will be written as y is equal to log of x because the assumed base is 10. And the next way you should get y is equal to log base 7 of x. Any questions on those two? Going once, twice, Thrice. We flip over the last side. We're not going to do all 6. We're going to just do 3 of them, and we'll be done. Good job. You guys are doing great. So now I'd like to graph logarithmic functions. You know the general shape. Let's discuss the transformations. What is the transformation of the logarithmic function in letter A? What's going to happen to it? Up 2. So if I move up 2, does that change the vertical asymptote of the graph at all? It does not change the vertical asymptote. So therefore, my vertical asymptote remains at asymptote of, we will say, x is equal to 0. The direction state that I should state the domain, the range, the asymptote, and then please put 1 point on the graph as well. So I was at a math conference not too long ago with Miss Rubel, and you guys know that I say asymptote, and it can be produced asymptote or asymptote. Either way is correct. But I was definitely in the minority at the math conference for people who pronounced asymptote. And I felt kind of awkward. Like, should I change or should I stand my ground? I stood my ground, folks. You know, it all depends on just who you've heard it from. But without a doubt, in the mathematical community, you often hear asymptote a lot more. It's a Greek word, and I took Greek when I was in college, and so that's the more traditional pronunciation is that, anyway, Hannah's like, Mr. Gens, graph the function. Gotcha. All right, so if I do plus 2, it used to go through the point 1, 0. Now what point is it going to go through? 1, 2. What's the domain? 0 to infinity. What's the range? All reals. What's the transformation for the next one? Right 2. Does that change the location of the asymptote? Yes. So the asymptote as the equation of x is equal to 2. Does that change the location of the point? Where's the point now located? 3, 0. What's the domain? And the range? Please, folks, notice this. It doesn't include 2, does it? Because you can never take the log of 0. And you can never take the log of a negative. That's what it comes out to be. That happens because of our understanding the exponentials previously. The last one, I have 3 transformations. What are the 3 transformations? Down 3, left 1, vertical flip. Okay, we've got all this. Great job. Does the down 3 affect the asymptote? Does the left 1 affect the asymptote? Okay, so I'm going to move left, the asymptote left 1. Asymptote, we're talking x is equal to -1. So if the point used to go through 1, 0, and now it's left 1 and down 3, I'm going to be at 0, -3. Domain and range. What have you noticed is always the range for the logarithmic functions, real numbers. The domain, now just recall, you also said that there's a vertical flip here. It doesn't change the range, but it sure does, affect the shape. So let's make sure we show that. Don't judge my graph. Domain. A1 infinity.